Cost of a rental car, $60 plus 20 cents for every kilometer driven. You saw this last year, and we probably talked about it being an example of a linear relation. You may not have got why, and that's okay. It was just exposing you last year. A relation is linear if there is a constant change in both the independent and dependent variables. We are going to talk about linear functions until you are so sick of linear functions. And the next year, we're going to talk about different kinds of functions. We just need to make sure you've got linear down pat because there's the easiest. Once you have those and you're good to go, then we'll go on to harder ones. What does it mean by constant change? Well, here's just a table of values. And how many ways are there to express a relation? 5. What are the 5? Coordinates, table of values, equation, I heard people say, graph, diagram. So they've chosen to give you a table of values here, and they've told you the distance and the cost. What I want to know is what's the difference in the distance? So from 0 to 100, how many did we add? Well, that's plus 100. To go from 100 to 200, plus 100. 200 to 300, and no big surprise now, 300 to 400. That's called constant change. And constant change is kind of a weird expression because what does constant mean? Stays the same. What does change mean? It doesn't stay the same. So it's kind of a weird expression. What it means is that it's changing, but it's changing by the exact same amount. So it's going up by 100 every single time. That value is constant. It's not doing 100, then 150, then 200, then 300. Those are other kinds of functions that we'll look at next year. Take a look over here what's happening with the cost. To go from 60 to 80, what are we adding? 20. From 80 to 100, 20. 100 to 120, 20, and the last one is 20. That's the definition of a linear function. It means both the x and the y have a constant change. They're both going up by the same amount every single interval. Again, next year we'll start to look at functions when this doesn't happen. Maybe this one's plus 20, and then plus 40, and then plus 80, and plus 100. That's not constant change. Linear function is when both the independent and the dependent variable have a constant change. From a graph, it's easy to tell if something linear because what does a linear graph look like? A line. Don't say the word straight. Straight line drives me crazy. To a mathematician, what's a non-straight line? A curve, and then that's not a line. So just a line. Don't say straight line. This constant change that we just talked about is called the rate of change. Or the slope of a line. Where have you heard the word slope before? Math and science. Let's take it out of school. Skiing is typically where you hear it, slope, because what does the shape of the mountain look like? So it should be straight lines. Now we know in the real world they're not because there's rocks and jagged stuff, but in essence they're pretty much straight lines going up. Linear functions are the only thing that have slope, and that's why slope is so important to this. When we go on next year, we're going to talk about other kind of functions, but they don't have slope because slope has to be a straight line. So if we look at generally this graph here, and this is the graph of the table of values on the last page, this is cost to distance. So we already determined from the table of values it was linear. How can we tell it's linear just by looking at the graph? Because the graph is a line. And why is it a line? Well, because the rate of change is coming from the amount we're going side to side versus the amount we're going up and down. So what we can do is form little tiny triangles. And if I keep doing that between point to point, what do you notice about the size of the triangles? They're the same. That's why it's called constant change. Change because the line is going up, constant because those little triangles are doing the exact same thing. We measure this rate of change, or this slope, by the abbreviation of M, which is such a weird abbreviation because slope starts with an S. So a little bit of history you don't need to know, but it's kind of interesting. famous French mathematician in the 1400s. His name was René. And the story was he was a boy genius, but he was also very sick. He had polio and a bunch of other diseases, so he was in and out of the hospital a lot. And the story goes that one morning he was lying in bed in the hospital, and he was super bored, and he was looking up at the ceiling. So go ahead and look up at my ceiling. And so the ceiling was like this, except it was tiled with squares. So now I actually want you to look down on the floor, because my floor happens to be tiled with squares. So he's looking up, but that's what it looked like, squares. And there happened to be a fly crawling along the squares. And he thought, that's interesting. And he started to count the distance the fly was going and the rate of change the fly was going. And he thought, well, if we somehow had a system where we could count these boxes really easily and assign them numbers, we'd be able to do some really interesting math. And so what do we now call the place where we plot numbers and give each box a certain number? The graph. And more specific, because there's lots of different kinds of graphs, is what do we call a graph like this? So what do we call these boxes that it's on when we have a set of axes? What do we call it? It's called a coordinate plane. You've probably heard that before. P-L-A-N-E, not like airplane. It's called a plane. Well, the actual formal name is called a Cartesian plane, which you might have heard maybe in grade 9, Cartesian plane. Because if you go on to math in university, you'll meet other kinds of planes that exist out there. But everything in your world will be on a Cartesian plane. Well, it was René Descartes who came up with the Cartesian plane. And so because he was French, we wanted to give homage to the French. Just like with trig, we pay homage to the Greek by using Greek letters. And who takes French in the room? Nobody's taking French? Who took French? So do you remember the word to go up in French? Way back in here, it's called monter, which comes from montagne, which is mountain. And monter begins with what letter? M. That's where it comes from. That's why we use the M. It's weird because it should be S, but it's not. And so what M is equal to is the rise between 2 points divided by the run. Rise over run. You're going to hear that 1,000,000 times over the next 2 units. And what that means is the amount that we went up and down, because that's rise is when you go up, divided by the amount we went side to side, which is run. Run is horizontal, rise is vertical. So we also call this the vertical displacement over the horizontal displacement. It doesn't matter which of those 3 you remember or you use to remember. It just depends on what your brain is. Lefties tend to like rise over run. Right people tend to like symbols. Completely up to whatever works best for your brain. You just need to know that it is the vertical displacement divided by the horizontal displacement. So when you are a skier and you hear a certain number attached to the slope of the mountain, that's what they're doing, is they're giving you the angle and the amount of slope that's involved with it. That's the definition of slope. Are you still with me? Let's actually do a calculation. It'll come later, but I want to do now that we have the example. So if I wanted to actually get a numerical value for the slope, all I'm going to do is look at one of these little tiny triangles. And it doesn't matter which one I look at because we already said that they're all exactly the same. And what I want to know is between those 2 points, how much did we rise and how much did we run? So what's the vertical displacement over the horizontal displacement? So if we look at the vertical, we were at 60 and we went up to 80. How many units is that? 20. And if you flip back, and I'll do it for you so you don't have to, that's what we were calculating here on the table of values. That's the vertical displacement. It's what did y jump by. If I want to do the horizontal displacement or the run, all I want to know is how much did we move side to side. We were at 0. We went to 100. How many units is that? 100. Can I reduce that fraction, 20 over 100? 1 over 5. That's what we call the value of the slope, and we're going to come back and talk about this value in a second. Still with me with slope? This equation is going to come back a bajillion times between now and June, and then it's going to come back about 5 bajillion times next year. This is called the equation of a linear relation, y equals mx plus b. And if you've noticed, it's on my wall. It's the first orange sheet from the door. You've probably looked at it, didn't have a clue what it was. It will be up there. It will always be up there. It's not a secret. It will be on your formula sheet for the exam, y equals mx plus b. Y is the dependent variable. And that's why we practiced last week identifying what was the independent and what was the dependent, because it matters which is on the left and right of your equation. Well, if y is the dependent, guess what x is? The independent variable. I already told you what m represents. What does m always represent in math? Slope. What is slope? It's a numerical value that talks about the increase of the angle of a line. It's what's that rate of change, how much is the variable changing. B is the only one we haven't talked about yet, and it's called the y-intercept. The y-intercept. And what that means is when x is 0. The y-intercept is wherever the x is 0 on the graph. And so we think of this in terms of called the starting value. And so I'm going to go back to that graph momentarily. And the b comes from the y-axis when x is 0. So this is where we find b on the graph, and we just want to know is what's the starting value? What's the value when x is 0? In this case, b equals 60. That's a dollar sign, although you can't see that now. Well, the reason it's 60, and this is what you did last year in grade 9, is you looked at these kind of relationships, is because if you drive 0 kilometers, how much do you still have to pay for this car? $60. Even if you don't even drive it out of the lot, if you just rented it and never got in it, what would you have to pay? 60. That's what that y-intercept represents, is what's the amount you'd have to pay before you've driven. So in the above example, if we wanted to give the equation for this car example, we would start with y. We would need to fill in m, which we'll fill in a second. We leave x, and then we just have to fill in b. So the way the equations work is y and x are always staying as variables, m and b are numbers. Well, we just calculated b. We got it right off the graph by looking at the starting value. What's the amount you have to pay even if you don't drive? $60. We also already calculated the slope. That was when we looked at that little triangle and the rise over the run, and what did we say the slope was equal to? 1/5. What's 1/5 as a decimal? So I could write this as 0.2x plus 60. Decimal or fraction doesn't matter. Well, let's talk about what this means. If we look back to the example, you pay $60 no matter what, and how much do you pay per kilometer? 20 cents. That's what the slope is equal to. It's the amount you're paying per kilometer. Whew, how are we doing so far? That was a lot of theory about linear equations. What you need to understand today is that this is the general equation for a linear relation. M and B are numbers that you either find off the graph or find from the table. And we're going to do some more examples about finding them in a second. That's what you need to know. Everything for the rest of this unit and next unit is going to revolve around y equals mx plus b. So example number 1. You need to be able to look at a table of values and decide, is it a linear relation? Not, is it a relation or function? That's what we did on Friday. We want to know specific, is it linear? How do you tell if something is linear? Well, it has to have that constant change. Both x and y have to have a constant change. So what we're going to do is look at the first column on the table. What are we jumping by every single line? So 0 to 20 is plus 20. 20 to 40, plus 20. This is good so far. 40 to 60, 60 to 80, and 80 to 100. Constant change for the first variable. But that's not enough. It's not enough just to have constant change for one. You have to have constant change for both. So we need to check the other one. How do we jump from 1 to 2? Plus 1. How do we change from 2 to 4? Plus 2. How do we change 4 to 8? Plus 4. I'm not even going to finish it off. What does that tell me? That is not constant change, and if it's not constant change, this is not linear. It's quadratic, which you'll meet next year. Turn to someone in front, behind, or beside you and tell them what constant change means. Amy, say what you said and say it again louder. They go up by the same amount. That's constant change. What's going to happen is you're going to hear constant. You're going to think, well, constant doesn't change. No, it doesn't mean it doesn't change. It just means it changes by the same amount. Do both variables need constant change? Yes, otherwise it's not linear. Turn to the same person. Together, figure out if B is linear. Okay, let's take a vote. Who says linear yes? Linear no. Oh, that was a pretty strong yes. Okay, prove it to me. Prove it's constant. So this time is always plus 60 for the A variable. Okay, so that's constant change. Plus, that's constant. Conclusion? Yes, linear. Let's just write some words for the wordy people, and I'm going to grab my red pen. If both the x and y variables, or independent, dependent, doesn't matter what you call them, so if both variables go up by constant amounts, the relation is linear. If both variables go up by a constant amount or constant amounts, the relation is linear. But if it's not linear, what is it? That's where we're going to spend all grade 11 and 12 showing you. What are all the other kinds of functions out there? We're just starting with linear because they're the easiest. They're just lines. That's the first skill you need, is to be able to look at a table of values and say yes or no if it's linear. The second skill is to do the exact same thing, but from an equation. And you have to do a graph, but that's easy. It's just a line. If it's not a line, it's not linear. How do you know if an equation is linear? Well, what is the general form for a linear equation? Y equals mx plus b. Do any of those values have exponents? Kind of a trick question. Do any of those values have exponents? Yes, they have exponents of 1. So that's called the degree, which you looked at last year. The degree of equation comes from the highest exponent. A linear equation has a degree of 1. A linear equation has a degree of 1. A linear equation has a degree of 1. If there is any exponent higher than 1, it is not linear. A linear equation has a what now? Degree of 1. If there's any exponent higher than 1, it is not linear. So take a look at I, or number 1. All you need to do is check the exponents. What's the exponent on y? 1. What's the exponent on x? 1. Or any of those higher than 1? Check linear. Number 2, what's the exponent on y? 1. What's the exponent on x? Ooh, is that linear? No. Well, what if it doesn't even have an x? Well, that's okay. You're still looking for a highest exponent. What's the exponent on y? Linear. 4 doesn't even have a y. We don't care. What's the exponent on x? 1. Linear. Number 5, check the x, check the y. Is there any exponent greater than 1? Conclusion? Linear. So now you have looked at a table of values. We have technically looked at a graph, and we have looked at equations. You need to be able to know all 3 of those things. Is it linear, yes or no? How are we doing so far? The last one you need to be able to determine is when it just gives you an explanation or a situation. A, just read to read. What's it about? Dog sled, that's all you need to know. Now let's pick out what's the most important step. We don't actually care it's a dog sled. We don't care if it's powered by dogs, by gas, by steam. We don't care. What do we care about? Speed, 10 kilometers an hour. The second sentence, they're describing the relationship. It's between what? Distance traveled and time. So how do you know? Well, there's a couple ways you can envision this and see what's happening, or you can start doing a table of values. It's completely up to you. You could also start to draw a graph. I'm a table of values girl, and I don't actually write this. I would do this in my head, but let's write it at the beginning. The time and the distance traveled. So the way I know if it's linear is I start to think, well, after 1 hour, how far has this dog sled traveled? Well, if it's 10 kilometers per hour, after 1 hour, it's gone 10. What about after 2 hours, assuming no dogs had to pee, nobody had to get water, didn't stop for any reason, it's still traveling the same speed? 20? That sounded like a question mark. Okay. 3 hours? 30? And then I stop and say, do those both have a constant rate of change? Do they have constant change? So how do we go from 1 to 2? Well, we added 1. And then 2 to 3, added 1. What's happening down here? It's adding. So is this linear? Yes. How do you know? Well, it comes from the speed, or if your brain works with a table of values, or if your brain works from a graph. It's completely up to however your brain works. Speeds are always going to be linear. Part B, read to read. It's about a square. Now tell me what about the square? We can do table of values, but we can also think in terms of the equation. So what's the relationship or the equation for area of a square? You've been doing this since grade 7. So length times width is a rectangle, but what do you know about a square? Both sides are the same, so we can call it length squared or width squared or side squared, however your brain wants to work. My brain works with side squared, but if you want length squared, that's fine. We'll take a look at the equation. What do you see? Oh, there's an exponent. Is it greater than 1? What does that mean? Not linear. So if your brain works with formulas, great. If you need to do a table of values, we could have done a table of values. Let's see how that would have looked. So we would have had the side length and the area. Side length of 1, what would the area be? Well, 1 times 1 is 1. Side length of 2, area would have been 4. Side length of 3, area would have been 9. Well, what's happening here? Plus 3 plus 5, is that constant change? No. So you can think of in terms of the equation, you can think in terms of table of values, you can think in terms of graph, however your brain's going to work. You're looking for constant rate of change or no exponents greater than 1. How are we doing so far? You're going to turn and talk a series of things. The first thing you're going to turn and talk is tell your friend, how do you know if an equation is linear? Whoever did not just talk, they're going to reply, tell your partner or your friend or whoever you're talking to, how do you know if a table of values is linear? Whoever talked first is going to talk last right now. Tell them, how do you know if an equation is linear? I think we did equation, didn't we? Yeah. Graph was the one I was thinking. Tell them how a graph is linear. Okay, how do you know if an equation is linear? No exponent higher than 1. How do you know if a table of values is linear? Increases by the same amount, constant rate of change, but more specific, both variables have to have, not just one. How do you know if a graph is linear? It's a line. So take a look at graph A and graph B here. Are these linear equations? I don't even need to read them, I just need to look. Yep, they're lines. So the second thing we need to be able to do is to go back to these situational kind of questions. We did these earlier in the unit, they just weren't necessarily lines. So we're going back to the same idea now in terms of lines. So read the little paragraph at the beginning before the graphs. What's important? Hot tub. Really, it could be a big tank, it could be a bathtub, we don't care, it's a vat. What's graph A about? At, ooh, key word here. Constant rate. Why is that important? Because that's telling you that it's linear. So even if you didn't get it from the graph, it says right in the question. What's graph B about? We're just going to answer questions about these graphs. We're going to identify the variables. We're going to talk about that rate of change that we kind of already talked about, and then we're going to get the equation for each one. By looking at the graph, I know, because I've done linear equations for 25 years now, that this emptied faster than it filled. How do I know just by looking quickly at the graphs that it emptied faster than it filled? Graph B is steeper, and we talked about the steepness of the line is rate of change. So that's telling me the rate of change is faster for the second one. By the end of this unit, you'll be able to look at that and just quickly know, oh, it had to empty faster. Why do things empty faster than they fill? Gravity's, right, pulling the water down the drain. Okay, part A, independent variable and dependent variable. Again, I use IND and DEP. If you don't like those abbreviations, you can use whatever you want. Quickest way to tell is the independent is the x-axis, the dependent is y. So independence along the bottom, dependence along the side. Independent is the x, dependent is the y. What's along the x-axis for both of these graphs? Time. And that makes sense because you can't control time. Time's going to tick on whether you're filling the tub or not filling the tub. What is dependent on the time? What is changing because time is going along? Volume. B is we want to actually get that rate of change. So we're going to do for graph A, and then we'll do for graph B. What is the one-letter abbreviation for rate of change? M. M is the same thing as slope, which is the same thing as rate of change. You can remember it as rise over run. You can remember it as independent over dependent. You can remember it as vertical over horizontal, whatever makes sense in your brain. How do we figure it? Well, we pick any 2 points on the graph. It doesn't matter which ones. I'm going to pick 0, 0, and I'm going to pick the one that's at 40. And what we're doing is creating that little triangle that we talked about on the example before. And why does it not matter what points I pick? Well, take a look if I picked 40 and I picked 80. What do you notice about that little triangle? It's the exact same size because it's constant, so it doesn't matter. So we need to know how much did we go up and how much did we go over? How much did we rise and how much did we run? What is the vertical displacement? How many units between the first point and the second point vertically? 800, I think I heard somebody say. What is the horizontal or the run? How much did we move side to side? We went from 0 to 40, so how many units is that? 40. Just like any fraction, we always reduce if we can. Can we reduce 840? Yep. So the zeros can go. And then what's 80 divided by 4? 20. Grabbing my red pen. The units is just like a speed. Any rate has to have something per something. Well, it comes from the rise over the run. The rise is liters. The run is minutes. So this is the liters per minute. What does it represent? It's the amount of water added per minute. It's the amount of water added per minute. Let's do the same thing for graph B. Still rise over run, that's never going to change. Pick any 2 points on the graph. I'm going to pick the first 2. Why? I don't know, because they're there. I could also pick the next 2. Doesn't matter, because those 2 little triangles are exactly the same. We need to know the rise, and we need to know the run. So what was the vertical displacement between 1600 and 800? How many units from 1600 to 800? 800. Except did we go up or did we go down? So I'm going to throw a negative in front. What is the horizontal displacement? How many units between those 2 little points? 20. Is that confirmed? Okay, can we reduce? Okay, zeros are going to go, and then what's negative 80 divided by 20? I meant negative 80 divided by 2. Negative 40. What are the units? Liters per minute. What does the negative mean? Why is it negative? Because the volume is going down. So this is the amount of water give me a good word here. What do we say when water leaves a bathtub? What's the typical? Draining, the water amount drained per minute. Remember I said I looked at the graphs and I knew right away it was draining faster? There's your proof. How much faster is it draining? Twice as fast, because we went from 20 to 40. How are we feeling so far on slope? Okay, let's get the equations. Graph A first. General equation is y equals mx plus b. Y stays as y, x stays as x. You have to fill in the m and the b. The m comes right from what we just calculated for slope. So for graph A, we know that it's 20. Where does b come from? Where does b come from? What does b represent? It's the starting value. So at the very start of the x-axis, when the time is 0, what's the volume? 0. Do I need to write plus 0? No. So the equation we would just say is y equals 20x. M is the slope, b is the starting value. Graph B. What's the slope that we already calculated? Negative 40. B is the starting value when the time is 0. What was the amount of water in the bathtub? Plus 1600. I'm going to highlight those. So here was the equation for A, and here is the equation for B. The rest of this unit and all of next unit is all going to be about what do these equations mean? How do we find them? What's the significance? Why are they important? Show me your thumb so far. Getting it, kind of getting, not getting it. Good. These are the things you need to be able to do after today. You need to be able to look at a graph or an equation or a table of values and tell me if it's linear, yes or no. The second piece is you need to be able to look at a graph, calculate m, and calculate the equation. How are we feeling? I'm going to suggest that you work with someone for this, or someone's.